last time we started to solve a wave equation, so I want to just remind you of the PDE. We have the boundary value problem here. You know, the one thing I'd mention is the main difference here is we have a second derivative with respect to time. Other than that, it looks exactly like the heat equation. And then the other difference is in the initial condition here for the string, we specify an initial position of the string and an initial velocity of the string. So that's a little different from the heat equation that we have these two levels of initial condition. And then here, the boundary condition there, that indicates the string at the left and right end are fixed and that their vertical height is always 0. So there's the right and left end never move. And so, you know, to begin the separation of variables, we can notice that the set of functions that satisfy the PDE and the boundary conditions form a vector space. So that allows us, and that's what I showed here on this slide, that allows us to start separation of variables. And you remember separation of variables is the assumption that our solution u of xt, which is the vertical position at any point on the string x and at any time t, we can write it as a function f of x times a function g of t. And of course, we assume that this is a non-trivial solution. And now we do the usual stuff. We plug in this f of x times g of t in for u on both sides here. And so we get this equation. You know, the only difference with the heat equation is here, this is g double prime. In the heat equation, we have just g prime. And we put the constant with the time domain problem as in the heat equation, and we separate the variables. And again, the only difference would be this extra time derivative that's not present in the heat equation. In the heat equation, we'd have 1 over k, some positive constant, times g prime over g equals f double prime over f. Okay, so that's the only difference. And you know, you can mathematically show it, or you can argue that on one side you have a function of t, on the other side you have a function of x. And so the only way this is possible is if they're both equal to a constant. And we call that constant negative lambda, just because it'll fit our intuition later. And so the boundary conditions, these boundary conditions, we have, you know, these, I guess, I don't know if I call them steady, but that's typically used for temperature stuff. But anyway, we have these trivial, you know, homogeneous boundary conditions that we can translate into a boundary condition on F here, on capital F. So this boundary condition translates to a boundary condition on F, and then we have this other boundary condition here. And the argument here is, so just by way of review. So if you look at this, for example, look at this equation, and you say, okay, well, there, f of capital L has to be 0. Why? Because if g of t is 0, then if g of t is 0, then our original solution will be 0, and that violates the non-trivial solution assumption. So here it's not possible for g of t to be identically 0. And so we conclude it's f of capital L that must be 0. So that's how we're getting to these boundary conditions. And so now we have time domain problem, eigenvalue problem, or, you know, x variable problem or space domain problem. And again, let me remind you here, the only difference from heat equation at this stage is right here on the time domain problem. We have a g double prime. For heat equation, it's just g prime. And that so far is the only difference mathematically, right? So now let's solve the eigenvalue problem. And, you know, I don't know, It's the same old song and dance, but maybe it's good so that it's a review. So I hope you'll find this boring. So here, I don't know what's wrong with me. I went ahead and did the lambda less than 0 case. I usually skip this. So here, I'm going to let lambda equal negative m squared just to make the notation easier because lambda is supposed to be negative. And we're going to let f be e to the rx. And then when you substitute it in, you get r squared equals, m squared after canceling the non-zero terms here. In our equation, this minus sign cancels with the minus sign here, so we just have an m squared. And so we can write the solution, the general solution is this linear combination of these non-zero exponential functions. And so now if we use the boundary conditions, I'll show you we get a trivial solution here. Here, if you let x equals 0, the exponential term disappears completely. Both exponential terms disappear. On the other side here, we set it equal to 0. And now you can move C2 over and get the conclusion that C2 equals negative C1. And so our solution looks like, here I've replaced this C2 with a C1 and then factor out the C1. And so our function looks like this. And so this function, so now, I plug in a capital L. So now I'm doing the other boundary condition. So here I've plugged in a capital L and set it equal to 0. And you see the capital L is right here, replaced for the X. And then we also replaced the C sub 2 with C sub 1, and then factored out that C sub 1. So this function, we've talked about it before. This function, you can actually write this. This is actually like a cinch. You remember the hyperbolic sine. Hyperbolic sine here is of x, I'll just do x, is e to the x minus e to the minus x over 2. So here, if you look at this term, this is like this it's the negative of this numerator term. So what we have here is negative 2 sinh of ml, and the sinh function, your hyperbolic sine function, is only 0. That's a terrible hyperbolic sine function. It's only 0 when the input is 0. And here, ml is not 0. So this term is not 0. So the only possibility is C1 is 0. And remember, C2 equals negative C1. So that implies if C1 is 0, then C2 is 0. So we have a trivial solution. So lambda less than 0 is not, is not a case that gives us non-trivial solutions. If lambda equals 0, then we can show, you get trivial solution again. I'll let you think about that. If lambda equals 0, just go back to the original ODE and say, so go back to this ODE and say f double prime here equals 0. So I have f double prime equals 0 here. And then integrate twice, you get f of x equals ax plus b. And then using these boundary conditions, you can show we have a trivial solution there. So the lambda greater than 0 case is the only case that we're interested in for these particular boundary conditions for the wave equation. Again, here, this will look very similar to heat equation. I mean, it'll look identical because, the eigenvalue problem is the same and the boundary conditions are the same. So we get these complex roots if we assume lambda is less than 0. then we use Euler's formula. So these functions form a basis for the solution, and any linear combination of these will also form a basis. Any linearly independent pair of linear, functions that are linear combinations of these functions. So using Euler's formula, we can rewrite these in terms of cosine and sine. And so, just like heat equation, we can conclude that for the lambda greater than 0 case, the general form of the solution is f of x is this linear combination of cosine of square root of lambda x plus c2 sine squared of lambda x. So far here, everything has been the same as in the heat equation. And maybe you've fell asleep at least 2 times. So now we check the boundary condition. F of 0 equal to 0. So let's think this through. I'm going to let x equal 0. So in particular, you have a cosine 0 here and a sine 0. Sine of 0, that goes away. The sine term disappears. Cosine of 0, well, that's just 1. Let me check my unit circle. And so we just have C1. And on the other side here, we have 0. So C1 is 0. That means this term here, this entire term is not there. It's looking like our solution for the x domain problem is only going to involve sine functions. If this were a heat equation, I'd say, oh, it looks like we're heading right for a sine series. Okay, but it's not a heat equation. So let's see what happens. So as before, the other condition f of L equals 0. So now only the sine term has survived. And we've replaced x with capital L. And so here, the only way this equation can be true is if the sine root lambda L term is equal to 0. It's not possible for C2 to equal 0. Why? Well, C1 is already 0. If C2 were also 0, then f of x would be a trivial, f of x would just be equal 0, and we'd have a trivial solution. And we're not, we're not allowing trivial solutions. So here, I mean, if we let C2 be 0, then it's trivial solution, then it's just not even interesting. So we assume the sine term is non-zero, and so we can conclude that root lambda L must be an integer multiple of pi. And so now we discover that there's not just one eigenvalue, there's infinitely many, countably infinitely many, and we can solve for the eigenvalue lambda sub n. Now we can say is n pi over L squared. And here I've dropped the negative roots because the sine function is an odd function. Sine of negative x equals negative sine of x, and negative sine of x is just a linear multiple of sine of x. And here, we're generating vector space. So we just want the unique terms. Anything that's a scalar multiple will be in that span and will be redundant. So we made a choice to just drop n equal to -1, -2, so on and so forth. So yeah, so here is our solution to the x domain problem for the wave equation. And up until now, this looks very, very, very similar to the heat equation derivation. There's nothing really different other than that we're using c squared in our equation instead of k, So now when you do the time domain problem, here's where it's slightly different. Mathematically, it's not hard. It's just different from the heat equation. Here, remember in the heat equation, by way of review, in the heat equation, we only have the one derivative. So here we just have the single derivative, g prime. And with one derivative, g prime, g of t ends up being this exponential function. But with two derivatives, this is just like the eigenvalue problem. With two derivatives, we don't even have to, so this is really a bit redundant here, what I wrote here. I say similar to the x domain problem, the cases lambda less than 0 and lambda equal to 0 yield trivial solutions. Actually, we don't even consider these cases at all because we already eliminated them when we looked at the X domain problem. From the X domain problem, we already know lambda equals lambda sub n equals n pi over L or whatever. Yeah, lambda sub n equals n pi over L quantity squared. So this sentence is kind of, it's true, but unnecessary. We wouldn't recheck these two cases. We already know these are not eigenvalues. So for the lambda greater than 0 case, it's just like the X domain problem. Here, negative lambda, this is a negative number. And so when we take a square root, I get complex roots. The only difference now is we have this term C, this extra constant that wasn't there before. Remember, C is the signal propagation speed. C takes into account the tension and the density of the material of the string. So again, the basis of solutions, are these complex functions. And again, by Euler's formula, we can write the general form of the solution as linear combination of sine and cosine terms. Root lambda, instead of X, it's in the T variable. And we have this additional constant C because, we have this C squared term that we purposely put on the time domain problem. And now, we use the fact that we know square root of lambda. We've already solved for this square root of lambda right here. We know is actually equal to square root lambda sub n. There's more than one of them. We know square root of lambda actually equals n pi over L. So now I'm going to replace it. So here, this square root lambda gets replaced by this square root lambda in both cases. And this, this is the work, this we found when we solved the X variable problem, the eigenvalue problem, the space domain problem. And so now we can put together a product solution, right? Our separation of variables assumption is that U of xt equals F times G, but now we have more than one F and more than one G, and they're coordinated by the eigenvalue. Like here, we can G sub n, which has the eigenvalue lambda sub n, that will match up with F sub n, which also has the eigenvalue n. And so the eigenvalues are coordinating these product solutions. I don't match up F1 with G3. F1 and G1 go together, F2 and G2. And so now we have infinitely many product solutions. At this stage, we've already found functions that satisfy the PDE and boundary condition. I think it's important to keep in mind at this stage, we've already found solutions, and that each one of these is a solution. So there's my, F sub n of x times G sub n of t, and then just for fun, I distribute the f of x function across the g of t function here. And so now this is what our product solution looks like. So this is a solution for each value of n. Each one of these is a solution where a sub n and b sub n can be any constants. And now we want to combine them all. Each is a product solution that satisfies each product solution satisfies the PDE and boundary condition. And so now you know what's coming. It's superposition principle. We now want a way to stitch together. So now any linear combination of those product solutions is again a solution. And so now we get, here's the big, formal series solution of the wave equation. All right, folks, we've solved two PDEs. in your PDE class. Yeah. Woo. So this is now our formal solution to the wave equation. It might be a little weird to look at because you're used to looking at the formal solution of the heat equation. So let's just talk about what's different from the heat equation. In the heat equation, the T variable term is not a wave. In the heat equation, we have a decaying exponential term, right? In the heat equation, we have something like e to the minus lambda sub n kt in the heat equation. And we love this term in the heat equation because it's a decaying term. It makes convergence so nice. So this would be for the heat equation. Oh yeah, check it out, everybody. Cursive. Bam. So for the heat equation, we have that exponential decaying term. But for the wave equation, we have this, to me, slightly disturbing trigonometric term. Why do I say trigonometric? It's not a decaying term. You know, so if you look at from the point of view of convergence, if you look at this part, there's nothing about this part of the series that would indicate that this series should converge at all. If convergence is going to happen, these terms a sub n and b sub n, that's where the convergence is going to happen. These are going to have to go to zero fast enough. If they go to zero fast enough, then we'll have a chance of convergence. But there's one final little caveat to this convergence discussion. Here, remember, each one of these product solutions is a solution. And in fact, yeah, this infinite linear combination is a solution, but also any finite combination. So here, instead of going to infinity, let me go all the way up to capital N, where capital N is some very big number. Then in this case, what you have will still satisfy the PDE and boundary condition, but doesn't have any convergence issues. Of course, we still have the initial conditions to worry about. And this finite sum may not be able to capture the initial condition. Okay, let's go back to the full formal sum with all the terms. And so now what work do we have to do is to find a formula for the coefficients. We know everything other than, you know, what are the value of these two coefficients. And this is when our Fourier series theory kicks in. This is why we started the class by first studying Fourier series. Here, when we plug in, so think about what I'm going to do now. I'm going to plug in 0 for t, for the t variable. Replace t by 0. So you know sine of 0 is 0. So this entire term right here disappears. That term's gone. And cosine of 0, as you know, is 1. So this term here becomes a 1. And so if we take a look at what's left, and just from our knowledge of Fourier series, we identify that as a Fourier sine series. And we know sine of n pi x over L forms an orthogonal basis. We can use orthogonality. We can find, you know, a formula for a sub n using the orthogonality. And we can interpret the Fourier, you know, we can interpret what does the Fourier sine series represent? You know, if you find the Fourier sine series of a function, we know that the Fourier sine series of a function represents the, you know, you take the original function and extend it in an odd way, and then look at the regular Fourier series of that, right? So this is the Fourier series of the odd extension of u of x, or it's the, you know, periodic extension of the odd version or odd extension of u of x. So here we can fall back on all of our good old-fashioned Fourier series theory that we know and love. And so now one of the we found a formula for one of the constants here in our formal solution. So now I'm going to take a derivative, because the other initial condition is that partial u partial t equals v of x. So here we're going to take the t derivative of this sum. And so the only terms that are going to be affected is the cosine n pi ct and the sine n pi ct. You remember the derivative of cosine is negative sine. And we need a chain rule here. The derivative of the inside will be n pi c over L. And so when I do derivative of the first term with respect to t, I get a sub n, and then you have the negative from the derivative and the n pi c over L. From the chain rule, here's the sine n pi x over L. That's just the same that I copied. And then this term here, that's the derivative. And now we want to do the derivative of the sine n pi. So the derivative of sine, as you know, is cosine. And chain rule, the derivative of n pi ct over L with respect to t is just n pi c over L. So you do the derivative of the second term. It looks like that. And we still have the same. In the x variable, it's just always this sine n pi x over L. That's the same. You remember the solution to the x domain problem only had sine here that survived after the boundary conditions. So here's the thing. What you should, when you look at this mess, what you should really just in your mind say to yourself is, this whole term is just a constant. This whole term is just a constant that depends on n. So in fact, notationally, we can rewrite this. Let me just rewrite this, and let me just call this, this new constant dependent on, let me just call it a sub n, and I'll throw on a tilde for lack of or maybe I should do a hat. A sub n hat. And here, just for fun here, let's just because it's just a constant here, let's just relabel it. And now if you look at it, it's not that different. It's basically the same form as this. Here, when we let t equal 0, we should get some type of familiar Fourier series. When we let t equals 0, this term will go away. You let t equal to 0, this term will turn into 1. And again, we're going to get another Fourier sine series with some weird looking constant in the front, but it's still just a constant. So here, let t equal to 0, then this term goes away completely. And this is equal to 1. So we get, again, the part that could be a little bit confusing is like, hey, what's all this mess? Don't worry about it. Just think of this as being a constant that's dependent on n, and we can even just relabel it for now, just if our eyeballs don't like it. So let's call this b sub n hat, b hat. And again, we have a sine series. We know by orthogonality, I can find the formula for b sub n hat. So here, let me do this in 2 steps. So here we know from the orthogonality, the formula for b sub n hat will be, 2 over L, integral 0 to L, the function, which is v of x, sine n pi x over L dx. But now bn hat is just this expression, and we want to isolate this term here. So I'm gonna, divide both sides by n pi c and multiply both sides by L. And so when we do that, we get a formula for b sub n. Here, think about where this 2 n pi c came from. Here, this L will go up when you move it to the other side and cancel. And then the n pi c will go down in the denominator position when we divide. So you get 2 over n pi c with the L's canceled out. So here, L cancels, L cancels. So now, here is the formal solution of the wave equation with the formulas for the constants. Yay! Yay! We solved another PDE. And I hope the theory is familiar to you. I hope the separation of variables, the checking the eigenvalues, then putting them together, finding the product solution, and then using superposition to get the formal solution. Remember, our formal solution is not a Fourier series. But then when we let t equal to 0 to check the initial conditions, we get Fourier sine series. And, you know, for the initial velocity condition, there we take a t derivative of both sides. That's being done formally. We assume we can do that to both sides. And then, you know, we come up with expressions for the solution. The other main issue now to address is, well, does this converge? And that answer, unfortunately, is not so easy to understand. So folks, let's look at the solution. I want to show you this. It's an important part of interpreting what's going on here. And so here there are 2 waves. There's a wave that's happening, a space wave that's happening in the x and u variable. Remember, u is the vertical position. But then there's also a time wave happening in the t and u variable. Okay, so here's my little diagram. Make sure you understand what the axes are. So u here, that's your vertical position, up and down. X, this is our horizontal position, you know, 0 to L, whatever. Our string, that's our spatial variable x. Now be careful here. T, this is the time variable. Okay, so that's time. All right, so let me show you. We're going to look at a string that's, you know, vibrating up and down. So remember, this string is not moving in space. Okay, so this string is just, you know, vibrating up and down. Its ends are fixed, and it's just doing its own thing up and down. But what I want to do is graph it across time. So here the string goes down, then the string goes up, then the string goes down, you know, and then the string goes up. Here's our kind of a vibration. So here there's one obvious wave, which is this actual string that's going up and down. That's a wave. That's our space wave that's happening in the x and u variable. And there's this sine pi x wave term here. Now the other wave is fix a point. If you fix a particular point, you know, so let's pick a point here and let's paint it kind of a, you know, a bright color, and just track the motion of that point as the string vibrates up and down. So here I, you know, artificially put in the time here. With t equal to 1, you see it's up, then it's down, then it's up, then it's down, then it's up. If we track that motion, that gives us our so-called, you know, this time wave. Here you see there's this wave in the t and u variable here. You know, so just kind of physically trying to interpret what's happening. You know, we have these 2 types of wave phenomena occurring in this solution to the PDE. I mean, physically, what's happening? Physically, what's going on? You tell me. Physically, is any of this match up with reality? How does a string vibrate? You know, other than using science, I'm not sure how to answer that question. So as I mentioned, and here I wanted to throw up the heat equation by way of review. So this is the formal solution to the heat equation. And here, remember, this term is a constant. That's using f of x as the initial condition. And here's the familiar term that occurs in our wave equation solution, but then here's a term that does not occur in our wave equation solution. That decaying exponential term is wonderful for convergence. And so the wave equation does not have this wonderful decaying exponential term. And yeah, this completely affects convergence. This does not, so now you'll see that convergence, sometimes it'll happen, sometimes it won't happen. It's a lot dicier proposition with the wave equation, how convergence works. So that's why, for me, I always, was trying to tell you to really enjoy the heat equation while you can, because it's very nice with the decaying exponential term. And so, however, even with all these issues, convergence is possible. It all really boils down to the coefficients. And remember, the coefficients depend on the initial conditions, right? A sub n is 2 over L integral of u of x times sine n pi x over L. And B sub n is some constant integral 0 to L v of x sine n pi x over L dx. So A sub n and B sub n all depend on the initial data. If the initial data is nice, then it's definitely conceivable that this thing will converge, And so, like I said, it's a little more less guaranteed than in the heat equation. The heat equation, we sort of made this blanket generalized statement. In general, if your data is nice, is fairly well behaved, you shouldn't have any convergence problems. So here we were probably going to have to be a little more careful with that, So another, so other than solving the wave equation PDE, this solution is important for another reason. From analyzing this solution, and we'll do that in a couple of sections, from analyzing this solution, we're actually able to come up with another solution technique that's known as D'Alembert's solution of the wave equation. And it's a solution technique that uses traveling waves. It still is a style of separation of variables, but it's a slightly different style of separation of variables. So this is the only part where we'll do something other than separation of variables. We'll look at traveling waves for a little bit, and then we'll go back to Laplace's equation and go back to separation of variables. So here we get the formal solution of the wave equation using separation of variables. And, we definitely have to think about what happens with the convergence. So I want to now specifically focus on one example and talk about what happens with the convergence in that case, and kind of, use an example with an actual function so we can actually look and see, will this converge? Will it not converge? Why isn't it converging? What if we change something, can we make it converge? Okay, so here we're looking at this theoretical guitar string. I'm assuming it's just fixed at the ends here, 0 to L. It's a very simple string setup. And here we have an initial position where we're going to pluck the guitar string either with our finger or with a guitar pick. And here we're going to assume the initial velocity is 0. So there's two possibilities here, that we pluck it with a guitar pick. And in that case here, this is more of a corner. And so it wouldn't be differentiable there. Versus if we pluck it with our finger, we're expecting it to be smoother, less of a corner here. So here we're expecting this initial position plucked with finger to be differentiable, right there at that where there's no corner. However, plucking with a guitar, we're expecting it to be not differentiable. So, these are two optional starting points here. I'm going to start with this. I'm going to start with this assumption here that we're plucking with a guitar string, because mathematically I can find the equation of each of these lines just using, what we know from pre-calculus. I just need 2 points on the line, and you can do point slope form and calculate the equation of each line. Okay, so I'll let you think about that. So here, in each case, u of x will be continuous. In one case, u prime of x will be differentiable everywhere. In one case, it'll be piecewise continuous. Okay. And we're going to assume the initial velocity is 0. If the initial velocity is 0, then the b sub n term of our wave equation solution will be 0. So remember, our wave equation has an a sub n term and a b sub n term. And so here's my initial position. I've just found this using the equation of a line. For example, if x is 0, then u equals 0, so that I get this end. And if x is h, then u equals a. I get that end. It's just the simple equation of a line. Similarly, for this equation here, if you let x equal L, then u is 0, which is what we're looking for. If you let x equal h, I get a times L minus h over L minus h. The L minus h's cancel. You get u of h equals a. So it looks complicated a little bit, but it's just like pre-calculus equation of a line. And so now if this is our u of x, I'm not going to do all the integration. I'm just going to skip right to the a sub n, the coefficient, the value of the Fourier coefficient. Okay. And what we did was we integrated, right? A sub n equals 2 over L integral 0 to L u of x times sine n pi x over L. And then you'd break up the integral into 2 integrals. You'd break up the integral from 0 to L, you'd go 0 to h plus h to L. And in each integral, you'd plug in for u of x the appropriate function. And then here you'd use a integration by parts and calculate the a sub n. Okay, so I don't know. I haven't decided if I should put it on homework. It's just, we've done so much integration by parts. I'm sure you're sick of it. And so after some rearranging, we can write the solution this way. Okay, so this is the coefficient now in our formal wave solution, a sub n, and b sub n is 0. So we've assumed 0 velocity, so b sub n is 0. So all right, folks, here is what the formal solution of this wave equation, where you have the motion of a guitar string, where the initial position with initial velocity is this, plucked with a guitar string, where at the center, essentially, we've, at this point h, doesn't have to be the center, at this point h, we've raised the string up to a height of a, and then we've waited for a second so that there's no initial velocity, and then let it go, and then it's gonna vibrate. So if you look at the solution, remember t is time. So here in our model, without any gravity or external damping force, there's no natural part of our formal solution that makes it decay to 0. Unlike with the heat equation, there seemed to be this mathematical part that decayed to 0. It was built in, that decay. So here, at least the formal solution, without gravity or damping force, as t goes to infinity, there doesn't seem to be any limiting behavior without gravity, without a damping force. Once we put gravity or damping force into the equation, that could change things. So that's interesting, if not a little bit counterintuitive. I don't know. So here's the guitar string. Let's talk about the convergence. We can write the solution this way. What you should notice is t and x are the only variables. Everything else is either a constant or is our index. Okay, and here on the other side, u is a function of x and t. And so you've got your time wave, you've got your space wave. So now let me try and show you that this is absolutely convergent. So what I'm going to now do is take the absolute value on the inside here and try and bound stuff. So right off the bat, you can see the cosine and sine term, we can bound with 1. In fact, this sine term as well. We can get rid of all of those. They'll all be less than 1. And all this stuff in the front here, let's see. This is all just a constant. So all of this stuff is just some kind of constant. So here, really, so let me get rid of this. It's really the only things that are going to really hang around is this n squared down here. And then right here, we'll have a constant. I'll just replace that with a constant. So that's what I have right here. There's the n squared, everything else we can bound by 1. And all of this stuff, that's just a constant, including the 2a, excuse me. All of this stuff, that's just a constant. So let's just call that m. So, in this case, we get lucky because we know this is a very well-behaved P series. We know this converges. So here we're going to get absolute convergence. So here we're going to get really nice convergence, But I mean, we got lucky, right? Because of the initial condition, when you use integration by parts, we ended up getting this n squared down here, And so here, because of the initial condition, we do have nice convergence. We have absolute convergence, therefore uniform convergence. So we expect this to converge to a continuous function, but at least the Fourier series part. So, however, look at this irritating thing. So here, and I'll stop here right after this, but this is really annoying. If you take 2x derivatives of the formal solution, so we would differentiate this sine n pi x over L term twice. When you differentiate the first time, you get an n comes out. When you differentiate it the first time, you get one n comes out. When you differentiate it the second time, another n comes out. And so we have this n squared term. And this n squared term is going to cancel with this n squared term. And the second partial of u with respect to x does not converge at all for our formal solution. So here I have a function u. It's a formal solution. It technically satisfies the PDE boundary conditions and initial condition. But if you actually look at the second partial of u with respect to x, that is a series that does not converge at all. So, the initial conditions and initial position in a wave equation are extremely important when we talk about the convergence. And as I mentioned, certainly if we cut this off and just stop at capital N, that will also give us a formal solution that satisfies the PDE and boundary condition and will be an approximation. It'll approximate the initial condition as accurately as we wish, because if you want a more accurate approximation, just make n larger. So at the end of the day, the convergence issues don't practically affect us because we're never going to use all infinitely many of the terms. And any finite collection of these functions we know satisfy the PDE boundary conditions. The only issue is the initial condition. If you cut it off, then you'll have something that approximates the initial condition. And depending how many terms you use, that'll be as accurate as you wish, or. So that concludes the discussion of wave equation. And I'm going to stop right here. I want to thank you for your time.